this video, I'll be giving an introduction to databases and why they are important. We won't be getting into using a particular database management system, or SQL, in this lecture. Rather, we'll be covering some of the basic ideas, concepts, and definitions, so we can get into those things in future weeks. Before we begin, I'd like to once again remind you that you should read over the required readings before you watch this video. These would be Chapter 5 and Knowledge Extension 6. We also have some recommended My Lab homework that ties into this video. Give them a try after you finish watching. So let's get into it. Now, the first question you may be asking, especially if you're not a computer science student, is why do I need to know about databases? That sounds like a technical thing that IT would deal with. Well, databases are used everywhere, and I do mean everywhere. We're in the age of big data, and businesses are tracking every little bit of data they can, and almost any digital interaction you have is in some way retrieving or storing data in a database. Anytime you view a website, data is pulled from a database to show you the content. For example, when you're using Western's OWL learning management system, all the content you see for the course is pulled from a database. When you submit an assignment or post on the course forums, it's stored in a database. When you view your grades on Gradebook, they're pulled from a database. Sending messages, such as emails or on Discord, buying things from Amazon, and even playing online video games all involve databases being accessed in some way. You may be saying that's great and all, but I don't need to know about databases to do those things. And you'd be right, if you're just a consumer of those services. However, we want to be a manager or even an owner of our own business. And to do that in a modern world, we need to use technology and information systems, which in turn means we have to understand how these systems work to make correct and good decisions. As I mentioned multiple times before, we need to understand technology so we can use it appropriately in our business. Or we could run into pitfalls such as using technology for technology's sake, or investing in technology that doesn't accomplish our business goals or objectives. With that in mind, why do businesses use a database? What objectives and goals do they accomplish? Well, first and foremost, they organize and keep track of things. Databases provide us with a facility to store our data in, and tools for transforming that data into information. This is our main goal, after all, in this course, and of information systems in general. Next, they help to automate the tracking and retrieval of data, allow for multiple users to access data concurrently. Concurrently in this case means at the same time. The potential for automation and enabling multiple users to access the database at once are key, and what really set databases apart from something like Excel and spreadsheets. Let's take a look at an example. Let's say your company wants to track all of the customer support calls. When we're just starting out, this might be doable by one employee in a single spreadsheet, like shown here. But what happens as our company grows and we start getting more calls and have more than one employee? Think of the nightmare it would be to have multiple employees trying to constantly update this one spreadsheet. Maybe Bob has a copy on his computer, you have a copy on yours, and Dave on his. They'd quickly get out of sync and would be a constant mess to keep organized, with multiple people inputting, editing, and deleting data. Also consider what might happen as we get more and more calls. The spreadsheet would grow rapidly, and it would get out of control quite quickly. This is why using a database is key for complex data storage needs. We need a system that can handle massive amounts of data and allow concurrent use by multiple users. The last reason businesses use database is to keep track of multiple themes. What do I mean by themes? We mean data related by a common concept or topic. For example, student grades might be a theme, as would student emails, or even student office hour visits. These would all be unique themes despite all involving students. Each one covers a different concept: grades, emails, and office hours. As a very general rule, and I do mean a very general, spreadsheets are good for storing single themes, while databases are ideal for dealing with multiple themes. Now, unfortunately, all too common practice we see in many small businesses is using Excel sheets like it was some kind of database, which just doesn't work out in the long run. This is often due to businesses not understanding the technology or not wanting to invest the time or money into creating proper databases and retraining their employees on how to use them. Here's an example of a single theme, student grades, stored in a spreadsheet. And this is a fine use of a spreadsheet. If this is just one professor dealing with one theme's grades for a single course, there likely won't be enough students to cause problems, and since the professor would be the only one accessing the data, there's no need for concurrent users. However, when we want to start adding in more themes, like logging office hour visits and emails, or if we wanted to allow more users to access the data at once, such as teaching assistants, we'd have to start moving to a database, like in this example here. Here we see Access Database storing student grades, emails, and office visits. And one great advantage of this is that we could pull up all of the data for a single student at once. Here we see the data for Andrea Baker. Think of the complex formulas we would need in Excel to do this, pulling data from multiple sheets, and lookup formulas, and all that. Whereas with a properly set up database, it could be done as easy as inputting the student's name. And that brings us to our next topic, content. What is content, you might ask? Well, it's any data or information of value. It's an asset or resource to our company. Recall that information is a resource. This could be things like data in a database, spreadsheets, websites, blog posts, tweets, forum posts, graphics, videos, log files, reports, and so on. Businesses want to track everything, and everything we track is content of some kind. Now that we know what content is, how can it be organized? We can look at organizing content in two ways: the management of content and the presentation of content. By management of content, I mean, how do we store it? How do we index it, catalog it, process it, and sort it? Simply dumping everything into a file or Word document would not be very useful, and it would drastically limit our ability to utilize the content or gain any kind of advantage from it. Well, we already talked a little bit about how this used to be done in the past in one of our early lectures. In the past, content or data was organized, stored, and managed in things like filing cabinets, card catalogs, and ledger books. Or if we go really far in the past, maybe even rocks or pottery. Nowadays, we tend to store digital content in facilities like databases and spreadsheets, which provide not only a means to store, but tools to manage and process content. Using these tools in an intelligent way allows us to transform data into information. And after all, once again, that is the goal of this course and information systems in general. The other way we can look at organizing content is by presentation. It's one thing to store and process data into information, but if we have no way to present that information to the right people in a meaningful way, it's useless. For example, let's say we wanted to present some data on the impact of the pandemic on Canada's GDP. That's something we explored in an earlier lecture. What would be a better way of presenting this? As a giant table of GDP by each sector from 2017 to 2021? Or what about this graph? Which one do you think is easier to see that impact? For me, I definitely think it would be the graph. Again, this ties into the characteristics of good information. Good information also needs to be presented in a good way and to the right people to be useful. The next thing to mention is that the presentation of content is normally handled by a content management system, or CMS for short. These are information systems whose primary purpose is to provide an easy way to present and manage information. You've likely used such a system before without even knowing it, as the end consumer of the information, rather than the manager. For example, a popular blog post content management system is WordPress, and you've likely read blog posts or sites that use this without even realizing that a CMS was involved. WordPress makes it easy for blog authors to create, edit, format, and display content without having any understanding of HTML or the database that's being used under the hood. It also handles publishing the content to the public as a web page. A more enterprisey example would be OpenText, a company based out of Waterloo, Ontario, here in Canada. OpenText provides an enterprise information management system that are aimed at managing the content internally for an organization as opposed to publishing it to the public on the web. OpenText products have some rather advanced features that go beyond the normal authoring and publishing of a CMS. These include seeking and searching for documents across a whole organization, automatically managing content, automatically archiving old content, and even some AI-powered content extraction tools. Now we know what content is and that it can be stored and managed in a database. We need to ask, what is it exactly that databases contain? What content is stored in them? Well, the textbook definition of a database is that databases are self-describing collections of integrated records. That's a bit complex right now, but essentially this means two things. First, that data in a database is self-describing. That means that in addition to normal data it stores, it also contains data we call metadata. This metadata describes the structure of the data contained in the database itself. The second thing this definition is implying is that data or records stored in the database are integrated. This means that the data is related or connected to other data in the database. Don't worry if this is all a little bit confusing, as we'll be diving more deeply into both of these concepts soon. The data elements stored in a database have a hierarchy to them. The hierarchy starts with the lowest level element, bytes. We can think of bytes as a single character of data. For example, if we were storing my name in a database, each letter in my name, including the space, would be a single byte of data. This means it would take 13 bytes to store my full name. So if you have a text file that is 1,000 bytes in size, that would mean it contains 1,000 characters, including any white space. Collections of bytes, like a name, are grouped into fields or columns. For example, perhaps we have a first name field and a last name field. Both would be a collection of bytes. The first name field would contain 6 bytes, one for each letter in my name, my first name that is, and the last name field would also contain 6, one for each letter in my last name. Going up another level, we have records or rows, and these contain a set of fields all relating to the same item. For example, for a person, we might have a record that contains fields like first name, last name, address, phone number, age, sex, email, and so on. So records are made up of multiple fields, which are in turn made up of multiple bytes. The example shown right now contains 7 fields. The next level is tables or files. And while we're talking about that, one thing I should mention is you see that a lot of these have 2 names. The reason for that is the terminology for these tends to change a bit between what software package we're talking about, or even what textbook we're using. So I've listed both for here, but they are interchangeable. So we can say columns or fields, we can say rows or records, or we can say tables or files. Anyway, as you might have guessed, tables and files are collections of records. For example, we might have a table that describes our employees like this. The table contains multiple records. Each row is a record describing one employee. Similarly, the fields become the columns of this table. So we have rows that go like this, which are the records, and we have columns that go like this, which are the fields. And the whole thing is a table or a file. So now you might be thinking that the next level up must be databases, right? Just like the lower levels, databases must be collections of tables. Well, not quite. Databases do indeed contain multiple tables, but they also contain more than that, and these extra components are critical. So not only do databases have collections of tables, they also contain relationships among the rows of the tables, as well as metadata, which we'll get into shortly. For now, let's take a look at an example and explore the idea of relationships. Here we have an example from Chapter 5 of your text, so you should be familiar with this already. This is a database created by a professor to track student grades, email messages, and office hour visits. Before we get into relationships, though, let's quickly review some of the data elements involved in this database. And this might be a good opportunity for a few mini activities. I'm going to put up a timer and give you a few seconds to look over these tables in this database, and I want you to try to tell me how many tables are here, how many tables are in our database. So I'll put the time up now, try to give it a little bit of a thought. And we're back. Let's take a look at how many tables there are. And this should be an easy one. We have 3 tables here: the email table, the student table, and the office visits table. Each one is a collection of records about a single theme or topic. Now let's look at this student table here in the middle. How many records are in this student table? Once again, I'm going to put up a timer. Try counting them. And we're back. So the student table has 8 records. Let's count them. 1, 2, 3, 4, 5, 6, 7, and 8. Now you might be saying, wait, but there's one more. And this is a common mistake some students make. This top row is not a record, as it doesn't contain any data. Also, we don't have a student in our class named student name. Rather, this is a type of metadata that describes and gives meaning to the fields in the table. In this case, this metadata are field names. They let you know what these fields are. Now, for our final question, how many fields are in the student table? I'll once again give you a few seconds. How many fields are in the student table? And we're back yet again. The number of fields in this student table is 5. Recall that the fields are the columns of the table. They describe a single attribute of a record. For example, the currently highlighted field are the students' names. However, we also have fields for student number, homework 1 grade, homework 2 grade, and the midterm grade. Now there's another thing I should point out here that we can see in the table, and that is we have a blank value. And this is perfectly fine if we allow it. We call these blank values null values. And we would say that fields that are allowed to be blank or null are nullifiable or are not mandatory. And controlling this, whether something can be blank or not, is something that we can set in the metadata or properties of our database. We'll get into that more when we talk about access, and a little bit in ERDs. Now, before we talk about relationships, we need to mention keys. Primary keys, in particular, are columns that uniquely identify a row in the table. Recall that columns are fields and rows are records. Every table has a primary key. Well, it might be more accurate to say that most tables have a primary key. There are a few special cases that we'll get into in later weeks where this is not the case. But generally, each table we'll be working with has a primary key of some sort. So let's take a look at the student table again. The student number is the primary key. Why the student number? It's the only value that's guaranteed to be unique. You might ask, well, what about the student name? We're looking at this data. No one in the example database has the same name. And while that's true, primary keys have to always be unique, not just for the current data that we're storing, but all possible data that we could store. Consider that's not unheard of for 2 students to have the same name. And we wouldn't be able to store them in our database if we made student name the primary key. So it's much better to stick with student number, as that's guaranteed to be unique. When we can find a unique primary key in our existing data, we call this a natural key. Looking now at the email table at the top, what would our primary key be? If we use date, we might have a problem. The primary key has to be unique. Making date the primary key would mean that we could at most store 1 email per day. That might be nice for the professor, cut down on his workload, but probably not so much for his students wanting to email him, as only one student could email him every day. If we tried instead to use student number, we'd also still face some issues, as this would mean each student could only ever email the professor once, and then never ever again. An alternative we could try is something called a composite key. Composite keys allows us to use two or more fields together as a key. This is sort of like gluing them together so they become one value. This means that the fields taken together have to be unique. For example, if we made both data and student number composite keys for this table, it would mean that each student could email the professor once per day, as we are now considering both date and student number together. The same student email on a different date would be considered a different value, a different key. This is an improvement, but it still has a few issues. Students may want to email their professor more than once per day, after all. So the solution in a case like this, where there's no clear natural key, and a composite key would still have issues or be too complex, is to add something called a surrogate key. What this means is adding a new field to the table whose job is to only act as the primary key. This field doesn't contain any useful information about the records, but simply contains a unique value, such as a number, that's guaranteed to be unique. In real life, at least, in my experience, surrogate keys seem to be one that we see used most often. They have the advantage of always being unique regardless of the underlying structure of the data, and they'll work even if we start making changes to the table. We don't have to worry about if that change is going to break our primary key, because we have a dedicated field just for it. Once again, these are called surrogate. And just like with that email table, the office visit table needs a surrogate key. Now that we have all our primary keys figured out, we can move on to foreign keys. Foreign keys are just what they sound like. They are keys that are in a different table than the one they reside in, and they are what makes relationships possible. Let's take a look. We already know that student number is the primary key for the student table, but we can also see that it appears in the email table and the office visits table. These are foreign keys. First, this may be a bit confusing. Emails don't have a student number, nor do office visits. Rather, the presence of these foreign keys serves to define a relationship between these records. For example, notice that the office visit record has a student number of 4867, and in the student table, we can also see that there's a record for a student with a student number of 4867. This match defines a relationship between the records that tells us that this office visit is related to Adam Verbra. It's important to note that unlike primary keys, foreign keys do not have to be unique. Notice that in the email table, there are two records with the same student number of 1325. And this makes sense if you think about it a bit. A student can, after all, send more than one email to their professor. So let's try applying this knowledge. Looking at this data and what we just discussed, can you tell me how many emails Andrea Baker has sent? And what was the content of those emails? I'll give you a few seconds to think about it. And we're back. In this case, we simply look at the records for Andrea Baker in the student table. And when we're doing this, we find her student number. In this case, it is 1325. Next, we take a look at the email table and look for 1325 in the student number fields. In this case, we find two matches. This means Andrea sent two emails. We look at the records we found these matches in, looking to the left in this case, and we can find the content of those emails. In this case, we have a question about homework 1 and an email that they sent to the professor about some group members. One last thing I'll mention before moving on is that these lines we see in this diagram are not stored in the database. They're just for illustrative purposes. Databases define these relationships through primary and foreign key fields, and the values they contain in records. And in many ways, they look up information in the same way we just did, by cross-referencing records in the tables. So recall this diagram from before. We have now discussed the tables and the relationships, but we still need to define metadata. Recall that databases are self-describing. This means that in addition to regular data, they also contain descriptions of its contents. This is metadata, that is, data that describes other data. This can be things like field names that we saw in the previous example, but also much, much more. The metadata makes databases far more powerful and easy to use. Here's a screenshot from your textbook of the properties for an access table. Access allows us to easily bring up properties for any table, and these properties are all metadata of some kind or another. There are things like field names that give names to each field in the table. We saw examples of this previously with things like student name or student number. Those were field names that we gave to certain fields. And we also have things like data types. This lets us know what type of data is being stored in the field. Examples would be numbers, text, ULRs, currency, and so on. It's similar in concept to the number formats we saw in Excel. We also have descriptions, which simply let us add a note to tell the users of the database what this field's for, what anything special they need to know about it, and things like that. It's not something that the database uses itself, rather it's just something that's displayed to users. And there are many, many more properties or metadata that can be set. And we'll be getting into all of this far more once we cover Microsoft Access in a later week. But for now, just recognize that this is all data that describes data, and that is called metadata. Moving on, we are now going to talk a bit about database management systems, which are also called DBMSs for short. So what's a DBMS? Well, it's software that we use to manage one or more databases. They make databases more accessible and useful, and they handle things like concurrent users in a safe way so that we only have to worry about data and structure of our database, not what's going to happen if two people access it at the same time. They provide tools for creating, querying, processing, and administrating databases, as well as managing the access, control, and security requirements of our database. Companies very rarely make their own DBMS. The only exceptions would be big tech companies that are trying to accomplish some very specific and niche objective. Most of the time, businesses either buy a license to off-the-shelf DBMS software made by vendors like IBM, Microsoft, or Oracle, or they use free open source software like Postgres or MySQL. There are many different kinds of DBMSs, but most of the common ones we see in use by businesses are relational database management systems. This simply means that they deal with relationships between records like we just saw. Access, the DBMS we'll be using in this course, as well as Postgres and MySQL, are all relational database management systems. One last thing I should stress is that databases and DBMSs are two very different things. Databases are collections of tables, relations, and metadata, while a DBMS is a software package used to manage a database. So we have one thing, DBMS, that's a software package used to manage another thing. That other thing would be databases. This diagram from our text gives us a good idea of where DBMSs sort of fit into things. The DBMS sits in the middle of things and handles requests from applications to access, alter, or update our database. In some cases, this request may be done manually by a database administrator, but in most cases, these requests are issued indirectly by users through database applications. For example, when you log into OWL and load up our course webpage, you are making OWL, in this case this is the database application, send requests to a DBMS, which in turn retrieves the data from a database and then sends it to OWL, to then format and display in your web browser. The DBMS in this example is likely Oracle or MySQL. Now we know a little bit about what a DBMS is, let's dive more deeply into what they do. DBMSs have three main functions. The first is creating new databases, their structure, and their elements, such as tables and relationships. Second is processing the database. This would be things like retrieving information, inserting new records, updating existing records, or deleting data. In most cases, this processing is done via a language called Structured Query Language, which is abbreviated as SQL. Bit of a side note, but there is still some debate about how SQL should be pronounced, and it seems to be a very regional thing. It can also alter based on what software package you're using. The most popular pronunciation seems to be SQL, but it's also common to spell it out, such as SQL. I tend to prefer the SQL pronunciation, but feel free to use either. Regardless of how it is pronounced, SQL is an important tool. It essentially allows us to ask the database questions, or as we like to call them, queries. And we do this in a language that the computer can understand. These queries can be quite complex and pull data from multiple tables and give us insights that might not have been possible otherwise. SQL is a great skill to learn, as it's more or less portable between the different DBMSs. If you learn SQL while using Access, like we will do later in this course, you'll be able to take that knowledge and use it to ask questions to other DBMSs like MySQL or Oracle with very few changes. The last function provided by a DBMS is administration. So administration can involve a number of tasks, but they're all supporting functions and not directly related to processing the data, creating the data, or collecting it. One of the most important of these is access control and security. Administrative functions allow us to control who can access our database and what permissions that they have when they do. By permissions, I mean what tables they can access, what records they can alter, and so on. You could imagine if, for example, we had an HR database that we might get some significant issues if employees could just freely access our database. HR tends to track a large amount of sensitive information, including salaries, reasons for medical leave, and other confidential information that needs to be carefully controlled. You can imagine the havoc that might happen if anyone in the company could read anyone else's records. Access control allows us to select who can read what and who can edit what. Another administrative function is backing up data. Having a good backup procedure is critical for any business, as well as you in your personal life. Any data of value must be backed up, both on-site and remotely. We'll get more into backups and how to do them in a later week. The last key administrative function is removing and archiving data. If we're tracking everything in a business, our database is eventually going to grow out of control. And this is a problem for a few reasons. First, storage costs money. We talked a little bit in an early lecture about some predictions about cloud computing and cloud storage becoming effectively free in the future. But we're not at that point yet, and in the real world, storage costs money. Second issue is that depending on how our database is set up and designed, having massive tables of data could eventually start slowing things down and making it harder to sort or search through the data. Solution to this is periodically removing or archiving old data. Recall that one of the characteristics of good information is timeliness. Keeping track of orders from 10 years ago and keeping them around in our database may not be necessary. Or at least we might not be needing those orders readily available and could archive them to prevent them from slowing things down in our database. Administrative functions help automate these archiving and removal procedures. So let's now move on to discussing database applications. And of course, the first question to ask is, what exactly is a database application? I've mentioned the words database applications a few times in this lecture, but I haven't quite defined it yet. So let's do that. Database applications are the software we create that actually utilizes our database. These are forms, reports, queries, and custom programs that interact with our database to produce, collect, display, and manage data. And a key thing here is that databases can power more than one application and each application can have multiple users using the application simultaneously. Let's take a look at an example. Here we see a diagram that shows three database applications: order entry, purchasing, and warehouse management. They're all powered by the same DBMS and utilize the same inventory database, and they do this all simultaneously. This provides some critical features for a business. First, the DBMS handles keeping the data synchronized. Bob from sales can input an order entry at the same time Alice is updating inventory, without causing any issues. No one is sharing a file back and forth, so there's no opportunity for things to get out of sync, and it's harder for users to break anything in a significant way. At least it would be if applications are designed correctly. The second advantage this brings is that we all have our data in one place. This makes backups easy, as well as security. Imagine if instead of a database, we were just shared Excel workbooks around the office. Who knows what computer they might be on, or who has access to them? Worse still, what if there are multiple versions of the same workbook? How do we know we have the most up-to-date one? Database applications solve this by making it easy to keep everything in one place. The next advantage is that database applications provide a simple GUI or graphical user interface for doing complex tasks. End users of these applications don't need to know about databases, SQL, or even what a DBMS is. They only need to be trained on how to use that specific database application. Lastly, keeping all the data in one place and maintaining relationships between the records makes it easy to do data analytics and analyze our data. Once again, recall that the whole goal here is to produce information from data, so having it all in one place makes that task a lot easier. Forms, reports, and queries are the basic building blocks of most simple database applications. Forms are used to provide users with a simple interface for reading, inserting, modifying, and deleting data in a controlled way. Forms provide a graphical user interface to predefined parts of our database that allow end users with little knowledge of databases to access and manipulate them. Here's a simple example of an access form for managing student records, and we'll be learning how to make this in a later lecture when we cover access. Reports provide a structured read-only output for a particular set of data in your database. They also have options for doing extra computations and processing on the data to turn it into information. This example, again from Access, shows us a list of doctor patients from the database, as well as their account balances. After a record is created, it can be easily run again to provide updated information. For example, you could run this report each month, print it off, and give it to your accounts receivable department each month. And this is a great thing for automation purposes. Once you've created this report once, to make it again, you just hit run, and you get a new updated report based on what's currently in the database. It could save a ton of time. Lastly is queries. These are how we ask the database questions. They can be created in SQL, or in some cases with specialized tools like Access's Query Builder, which we'll see example of right here. In this example, we're asking the database for a list of all tests ordered by all doctors. The results would look something like this. This doesn't look too impressive right now, but it is pulling data together from 3 different tables. The equivalent SQL would look something like this. Queries are used more by database administrators and programmers as opposed to end users due to their complexity. They tend to use them more indirectly through database applications. Now don't worry if you didn't understand these little screenshots have been popping up. We will be covering this in far more depth in later weeks, where I'll actually go through and explain what all of these are and how to use them. In addition to forms, queries, and reports, we can also create our own database application programs from scratch if we have a need for a specialized tool or service. These can do things like turn content from our database into web pages and web services, as well as gather and track data over the web. Most websites you use are likely some kind of database application program that serves its content as a web page. Amazon, for example, is using some kind of database application program to pull products from its database to display to you and allow you to order them, which in turn updates their database. This is all done transparently to you as the end user. While this may look like a web page to you, in reality it's a specialized kind of database form that's being served to you over the internet through your web browser. Visualizing this would look something like this diagram here. We have our DBMS and database, which manages and stores our data, which we've already covered. And now we have application programs running on a web server, which connect to the DBMS and request data to turn it into a web page, as well as providing a means for end users to alter or update the database via the DBMS. Finally, end users connecting to the application programs using a web browser on their computer. From end users' point of view, they're simply connecting to a normal website like Amazon, Discord, or Owl. But in the background, they are using a database in a very controlled way. Our last topic in this video will be Microsoft Access and how it differs from a traditional database management system. In this course, we'll be using a database management system called Microsoft Access. This is a bit different than some of the DBMSs we've been talking about so far, like MySQL or Oracle, as Access is a personal DBMS, while the others are more enterprisey or enterprise DBMSs. So what is an enterprise DBMS? These are DBMSs that are not typically installed locally on the end user's computer, but on servers running in the company's data center or alternatively in the cloud. End users would only connect to them via database applications that are independent of the DBMS. Enterprise DBMSs are designed to handle large numbers of users and many different database applications all concurrently. Some examples are IBM's DB2, Microsoft's SQL Server, and Oracle's Oracle DBMS. Personal database management systems, on the other hand, are designed for smaller and simpler database applications. They support far fewer users, normally between 1 and 15, and these are often installed right on the user's computer, and the data is either stored locally or on a network share of some kind. While they might not be as powerful as enterprise DBMS, they are far simpler to use and configure, and they don't necessarily require any server infrastructure. They also tend to come with the tools to easily build your own forms, queries, and reports without any programming knowledge. Enterprise DBMSs, on the other hand, tend to only provide a simple SQL or command line-based interface, and applications are developed independently by programmers. Nowadays, there are not many personal DBMSs remaining, and Microsoft Access is one of the last ones. However, this doesn't make it obsolete. It still plays an important role in business for when you need to make a simple database fast, or without requiring much database knowledge. It's also great for educational use, as students can have their whole DBMS and database on their own home computer without any complex software installation or configuration steps. To visualize this a bit, we can see that one of the main differences is that Microsoft Access provides both the DBMS and tools to make forms, reports, and queries in one package, while traditional DBMSs tend to keep these more isolated, as we just discussed. So that's all I have for you in this video. This week we'll be investigating entity relationship diagrams and how to start planning and describing these databases through a series of tutorials. In the coming weeks, we'll start using Microsoft Access and getting into actually creating and using databases, as well as database applications like forms and reports. Later still in the course, we'll be learning about SQL and using it with Access. Your next step after watching this should be getting started on those ERD tutorials. And I highly recommend doing them with a piece of paper and a pencil so you can follow along and sort of draw the ERDs as I describe what we're doing to you. My suggestion would be to, whenever there's a new step in the tutorial video, pause it, try to solve it yourself on paper, and then unpause the video just to see if your solution matches up. I think you'll get a little bit more of the videos if you're following along closely like that than just watching them as a passive experience. Anyway, thank you for watching and have a great day.